Okay, good morning. It's a great pleasure to introduce today's speaker, Fabrizio Fiore. Fabrizio is a colleague, is a friend since many years. Many years. I mean, there is no need to enter in details of how many years. He's actually the director of Observatory of Trieste Observatory. He was previously was director in Rome in Monteporzio. He was scientifically born as an high-energy astrophysicist, and he worked on essentially all X-ray missions since, I would say, Exosat or something like that. Name a mission, and he got it. He provided a relevant contribution in the field of extragalactic astrophysics, mainly AGN and gamma-ray bursts. There is also no need to review his CV. He's a scientist, but he was always curious about technology, so he followed all the time in his career technological developments, and also very open-minded with the wide interest. And today he will tell us about space science and the space economy. Fabrizio, please.
Thank you very much, Andrea. It's really a pleasure to be here among a lot of friends. So this talk is a bit different from the usual presentation that probably you are used to. So I apologize at the beginning for this. Most of the stuff I will present is from this paper written with Martin Elvis, but I also will present something more with respect to this paper. So this is the question, very simple question from which we started. Will it be possible in the future to realize large, complex, basic science missions like HST, Chandra and JWST? And if yes, how? Well, the timing of this question is particularly well suited because today, space-related investments have grown exponentially in the recent years, exceeding $500 billion last year, when, for the first time, private investment surpassed the government investment. And of course, these missions have been done using government investment. So the question is, can space science take advantage of the benefit of the new space economy to reduce cost and development time, and at the same time succeed in producing powerful mission in basic science? So we were discussing with Martin these things, these ideas, let's say 1.5 years ago, and most of the stuff in the paper was written in Aspen at the end of August last year. And of course, when we were writing these things, we were considering that Trump was winning the election in November. But of course, we were thinking that this second Trump administration was going to be similar to the first Trump administration, in which basically not much happened about science. And in fact, we were very wrong. This is what happened a few months later. In yellow, you can find the president budget for NASA, in which basically the money that NASA was going to put on science were reduced by half. But if you look at astrophysics, they were reduced by 2/3, which means that basically most of the missions in operation should be closed, and most of the missions in preparation should be closed. So this is not just a, let's say, 20% cuts that can be bad, but you can survive. This is a change in the way science is considered in the US. In fact, similar cuts have been proposed for the NSF. And the budget of NSF, the proposal was to cut in half the budget of the NSF. And for astrophysics, basically, the budget was zeroed for NSF. So this is the situation that happened, that is changing things. Here in this table, you can find also the proposal of the Senate and the House, which reestablish, in a sense, the budget for science at NASA. But as you well know, these proposals have not been accepted yet. And there is, in these days, the closure of the public administration in the US. So we don't know what is going to happen. If I speak with my colleagues, they are telling me that they are working till the end of the year, but they don't know what will happen in next year. So this is something that I don't know if these cuts will be implemented, but in any case, what I think is interesting to consider that there is a change in the way in the US. I don't know if the majority of the people, but a large fraction of the people is thinking at basic science. And therefore, I thought it was interesting to review which is the birth of the American scientific vision, which is put under very pressure in these days. This letter is basically the birth of the American scientific vision. This is a letter by President Roosevelt to Vannevar Bush, who was the director of the Office of Scientific Research and Development. This letter is from, as you can see, November 1944. In this letter, President Roosevelt is asking, what can be done consistent with military security and with the prior approval of military authorities to make known to the world as soon as possible the contribution which have been made during our war effort to scientific knowledge? Second, with particular reference to the war of science against disease, what can be done now to organize a program for continuing in future the work which has been done in medicine and related science? What can the government do now and in future to aid research activities by public and private organizations? The proper role of public and private research and their interrelation should be carefully considered. Fourth, can an effective program be proposed for discovering and developing scientific talent in American youth so that the continuing future for scientific research in this country may be assured? This is Vannevar Bush, and this is the report that was sent a few months later to the president. Of course, President Roosevelt died, and therefore the report was received by his vice president. And in this report, which I would strongly suggest you to read because it's really, I think, wonderful, Vannevar Bush says a few things which I just cut and paste here. Who was Vannevar Bush? Vannevar Bush was the director of Office of Scientific Research and Development, which is the organization that managed all research and development activities during the war, including the Manhattan Project and many other things like the invention of the radar. The starting point of the report, the first line is scientific progress is essential, capital letters. Then he says progress in the fight against disease depends on the flow of new scientific knowledge. Responsibility for medical research lies with medical school and university, which must be funded, financed for the most part directly by the government. Full employment can be achieved through the creation of many new business, but this must be based on new principles and a new concept, which in turn derive from basic scientific research. Basic research is scientific capital, the real reservoir for the production of new scientific knowledge. Establish a new agency. So this is the proposal to establish a new agency to achieve all these goals. And in fact, the new agency is the National Science Foundation, which started in 1950. The latest budget for the National Science Foundation was 8 billion for basic research, which for us means LIGO, Vera Rubin, Gemini, Kid Peak, NRO, JVLA, ALMA, so on and so forth. So the proposal of the Trump administration is to zeroed all this research for astrophysics paid by the National Science Foundation. So this is why I think this is not just an event, it's a revolution, it's a change in the way of thinking at science, innovation, and progress. And this is the link to the report, which again, I suggest you to give a look because it's really wonderful. Let's go back to the real talk. The real talk, this is the outline of the talk. I will start from basic science from space. And here I'm collecting the 4 themes that emerged in the past 25 years, the 4 main themes: exoplanets, black holes, galaxy scaling relations, black hole direct imaging, the accelerated expansion of the universe, multi-messenger astrophysics. These themes produced 11 Nobel Prizes so far. So these are the stuff on which we are working today, basically. Now, the 4 themes were not among the main scientific drivers for NJST, now called James Webb Space Telescope. In fact, in the decadal report, Astronomy and Astrophysics in the New Millennium, you can read that NJST is designed to detect the light from the first stars and to trace the evolution of galaxies, which is something that JWST is doing very well, as we all know. But you can also find other things. It will revolutionize the understanding of how stars and planets form in our galaxy thanks to Kuiper belt objects. I don't know how many of you are looking at Kuiper belt objects with JWST. Maybe this. So point is that when JWST was proposed, the main 4 themes in which we are working today were not on the table. 40% of the time of JWST today is dedicated to exoplanets that didn't exist when JWST was proposed. Of course, JWST is doing a great job on all these 4 main themes, and the reason is that basically JWST is an observatory, multi-purpose observatory, which is pushing the sensitivity by orders of magnitude with respect to everything that we had before, as you well know. But this did come for free. The cost of JWST was huge, the order of $10 billion, which means that it cannibalized all other astrophysical programs. For example, the program Beyond Einstein. The development time was very long, 23 years, and it was a very, very risky mission. And this is the famous cartoon showing the origami unfolding of JWST. 300 single point failure. If just one of these movements failed, $10 billion were just washed out. Today, we are talking in the Astro 2020 Decadal Survey of another large space telescope, the Habitable World Observatory, HWO, with a development time the order of 20 years, again, an estimated cost of 10 billion, so similar to JWST. So the point is, by the time HWO launch, somewhere in 20-25 years, new scientific teams are likely to emerge, as happened in the past. And the exoplanet may fade away in relative importance. Will the discovery space of HWO be large enough to accommodate other breakthrough discovery, as happened for JWST? So I think this is an important question that everybody should think on. And even more important, would NASA and ESA be willing to or able to embark on a new JWST scale project? This is what happened before the Trump revolution. Before the Trump revolution, in April last year, NASA paused the original JPL-led Mars Sample Return project. And Mars Sample Return project was again a 20 years, $10 billion project. In July 2024, NASA ended the Moon Viper rover project. And therefore, the question, I think, is very natural. Can HW and Artemis, the return of the man on the moon, man and woman on the moon, and Mars sample return coexist? Now, we have alternatives. One alternative to expensive multi-purpose observatories is to have multiple dedicated missions. And there are lots of very good examples on this, both at NASA, the Explorer programs, MEX, MIDEX, and even at ESA. In fact, Gaia today is the most productive observatory in the world. It produces 2,000 papers per year. HST is producing 1,000 papers per year. JWST less than that. So Gaia today is a dedicated project, but it is the most productive observatory in the world. TESS is a MIDEX mission, the Explorer program, is very productive, the order of 500 papers per year. Even a small thing like XPE, X-ray polarimetry, very niche program, is incredibly productive. In fact, it won the Rossi Prize last year for its discovery. Here, it is a plot that I like a lot on one of the main results of XPE, that is the fact that the corona in AGN is probably not a lamp post, but it's something that's stagnant on the disk. But of course, it is a very much hardcore X-ray astrophysics. So small things. Now, let's switch to the new space economy. When I present this, I start from this very nice plot, which show you the time that some technology took to arrive to the majority of the population. And as you can see, for example, the time that automobile took to arrive to the majority of the population was pretty long, but the time that cellular phone or internet to arrive to the majority of the population was very short, a few years, only a few years. And this is the new space economy. We are starting from very small, but the growth of the new space economy is exponential, as it is shown in this plot, showing the money that are involved in the new space economy as a function of the time. And as you can see, we are reaching, we reached half a trillion, and we will reach 1 trillion at the end of this decade. This is the latest report, which you can see that last year, $600 billion were involved in the new space economy. Where are this money going? This is a good question. This is a complicated table, but I will try to explain. Now, this is in this table you can find the amount of money that are spent on the space of the new space economy today, and the amount of money that are predicted to be spent in 2035, so in 10 years from now. So this is 630, and the projection is to triplicate this amount of money. But where are these money spent? Here you can find in this table 2 columns, backbone and reach, which basically means upstream and downstream. Upstream is what enables business, and downstream is the real business. So you can see that the amount of money, the largest amount of money are on services and user equipments, and in particular on a voice, which is an acronym that is PNT, and I don't know how many of you know what is PNT. Position, navigation, and timing. It is the GPS that is on your cellular phone. This is by large, as you can see, under the reach column, by large, the most important voice in the new space economy. Today, about $200 billion are involved in PNT business, and this number will reach 800 in 10 years. So this is the main, really the main business today. Of course, infrastructures are also very important, and also very important is defense. This plot was done before the, let's say, big emphasis on the increment of expenditures on defense, both in the US and in Europe. So you should probably multiply by a lot this number. Another very interesting plot when you speak about the new space economy is this one. This is showing the money that are put in space activities by venture capital or private equity capital. So this is money that are put by people or funds on startups. And as you know, when you put money on a startup, you are pretty much sure that only 1 out of 10 will succeed. So these are very, very, very risky investments. So this money grow from basically 0 to 8 billion per year in 10 years. And today, the investment is the order of 8 billion per year. Again, these are very, very risky investment, and who works in financial things, of course, uses venture capital investment as a proxy for the capability of a business to grow in future. So here there is, even in the standard financial environment, the thinking that space is going to be the next big business. Business in space, however, is enabled by resources. Today, you can find in the standard literature which are these resources. The main resource is location. Location is a key resource. In space, you can do things that you cannot do on Earth, for example. Another resource in space is solar light. Of course, you can use solar light with solar panels to power your satellites or to produce energy. And also in future, materials will be important, will be an important resource. Today, we are not yet at this point because we are not yet mining the moon or asteroids or Mars, but maybe in 10 years, yes. However, the standard literature misses a crucial point. That is, knowledge always enable harvesting of all other resources. And the point that I want to make strong is that basic science researchers, us, are the best suited to produce knowledge usable for space enterprises. So far, in astrophysics, we were not able to sell our knowledge to business enterprises. We publish papers that everybody can read if they are open space. But usually in astrophysics, we are not used to have a relationship with the business world. But in other kind of science, this is not true. And I think we should try to change our vision on this very important point. Innovation paradigm. There are 3 pillars for innovation paradigm. The first is technology innovation that is proceeding both through disruptive innovation and incremental innovation, as shown in this graph. You have moments in which innovation is proceeding very fast, and then moments in which you consolidate what you have found. And this happens again and again. Business innovation, which is defined as vertical integration, but even more important by scale production, mass production, and service-oriented business model. I would like to put emphasis here for the rest of the talk on the mass production. This is going to be the game changer, I think, also in our work. Third, probably even more important than the other 2 points, is cultural innovation. Startups must have a bold risk culture, which manifests in risk openness project management model. That is, for example, in this kind of agile model, in which you are looking for the minimum viable product, not the best possible product, but the minimum viable product at the end of each sprint, which is at the end of each cycle of production. This is a big change with respect to what we do now today on scientific basic science missions. Strategic versus commercial paradigm. This is a comparison between the 2 paradigms, the one on which we were working for the past 50 years and the one which I think we should learn to work in future. The 2 main points are this one. In the strategic paradigm, there is a geopolitical influence, no risk, no incentive to bring down costs, and even more important, military advantage. In the commercial paradigm, the most important thing is to make money, of course. Low risk, low cost, and risk openness. And you are looking at quality of life, wellness, which is proportional to innovation. And I would like, when I was doing this talk other times, this was one of the most controversial points. And I would like to spend 5 minutes discussing more in detail this point, because I want to be very clear to show which are the implications for us of this change of paradigm. Let's start from the strategic paradigm. Most space astrophysics has been founded so far by government under the strategic paradigm, with clear connection synergies with military programs. And in astrophysics, we have really many examples. For example, HST shares common design with the national recognized office KH-11 Cannon satellite. Actually, to say that shares common design is an understatement, because HST uses the same 2.5 mirror of that spy satellite. And in fact, this mirror was improved in the time, and Roman will use a new lighter mirror, 2.5 mirror, that is donated by NRO to NASA, basically. So this mirror was done not to look at stars or galaxies, but to look at what let's say, enemies of the United States were doing on ground. Of course, infrared detectors were developed for military purpose, not really for to look at high redshift galaxies. Swift fast repointing was developed by military purpose, and this is something that is well known. What probably is less well known is the history of JWST. There is a very nice paper written this year. It is in the references that I will leave you, which tells you why we did the JWST. Now, JWST segmented beryllium mirror, primary mirror, were developed jointly by NASA and the Department of Defense in the United States under the Advanced Mirror System Demonstration Program. This program started at the beginning of the 90s, so well before the NGST proposal to the Decadal Survey. In fact, JWST, the first idea of NGST started at the half of the 1980s, and the first ideas were actually by Riccardo Giacconi. This table compares technology improvements in JWST, JWST implementation, and synergies with the militaries. As you can see, the lightweight beryllium mirrors that we use with much let's say, results in astrophysics are used in drones and are used in satellite missile warning systems. Even more important, the cryogenic stability of this mirror These mirrors were done in beryllium because of this, because it is very stable, thermally stable. This is a key things to do, for example, missile seekers and space-based infrared system for ballistic missile defense. Segmented deployable mirror support scalable foldable optics for most satellite or deployable arrays in contested optics, which are used for surveillance satellites. And of course, adaptive optics is very much used for laser weapon systems, like, for example, Helios. So what we are using with a lot of fun is basically, it is a very good example of what is called today dual technology. Okay, so the point is that it is not true that we will do dual technology research in future. We have done this for the past 30 years. Maybe we are not aware of this, but this is the point. This is the first design of JWST. You see, it was not a segmented mirror. It was a borosilicate lightweight mirror with an elliptical shape. This was proposed in 1996, and this was the design that was pushed by Riccardo Giacconi. And the size of the mirror was basically 8 meters by 4.5 meters, and it was fitting in the shroud of an Ariane 5. And this is the design that was suggested by TRW under the study that was made both by NASA and by the Department of Defense in the United States, which were then, from which you arrived to the final JWST design. And the decision, the trade-off decision between the two was basically that the lightweight beryllium mirrors were very much something on which the defense in the United States was pushing. Commercial paradigm. Here I make an example from another field, that is geology. In geology, it happened very interesting things, that large energy and oil and gas companies, Exxon or your favorite company, spent a huge amount of money, 10 trillion in the past 80 years, doing oil wells. They produced more than 4 million oil wells. And the important point is that by a public-private agreement, all the data, drill bits, logs, everything was made public 2 to 5 years after the drilling. And this data was used to have the best knowledge of the geological history of the North American continent. It was used to study plate tectonics, mapping structures such as fault and sedimentary basins. So basically 99.9% of what we know about the geology of North America was done because it was paid by oil and gas companies. Of course, geologists offered in kind their work to balance the exchange. And in fact, public entities offer free expertise in exchange of data. And this reduced the cost for private entities and accelerated the research. This is an example which shows how it was studied, the Rocky Mountains on the Canadian side. And it is interesting, this is the slice that is cut along this black line. And this is what I wanted to show is this red segments are the wells that were drilled, and they were 4 to 5 kilometers. Each of these 4 million drills were very, very deep, and they were able to find all these faults and to even to arrive to very deep what is happening in very in depth under the Rocky Mountains. So in other scientific communities have already, I mean, by decades, worked with the privates in a way that is very convenient for both private companies and research, basic research institutes. Let's go back to our beloved space. This is a plot showing the launch cost as a function of the year. And you can see that actually the launch cost of the Saturn V at the end of the 60s, beginning of the 70s, was not too bad. And of course, it increased a lot with these. Let me be polite with the space shuttle. Then the price went back again 10 years ago, mainly thanks to the SpaceX Falcon 9 and Falcon Heavy launchers, and the price will go even lower with Starship, for that is predicted to put in space 1 ton at the cost of $200,000. Now, today, with $200,000, I can send in space a CubeSat. In a few years, I will be able to send in space something like Beposax. Beposax was weighing 1.4 tons. So this is the change, factor of many, okay? This is Starship, and the Starship revolution will not be limited to cost to orbit, because Starship performance will make it unnecessary to spend time and resources to minimize mass and size, because it's so big that you should not put a lot of effort in minimizing mass and volume. You should avoid these extremely complicated origami unfolding of JWST with Starship. Satellite cost. This is the I calculated the cost per kilogram of these missions. JWST, 1.4 million per kilogram. Euclid, not too bad, 0.76 million per kilogram. XP, SMAX, 0.4. Scientific CubeSats, 0.1. Standard CubeSat, 0.1. Starlink satellite 0.001 or 0.000, so a lot of zeros. You see, commercial satellite, the cost of commercial satellite is unbelievably smaller than the cost of dedicated scientific satellites. So there is a lot of margin there. So public funding, pros and cons. Of course, with the public funding, we can make our below the basic science missions, and funding are more stable than in the private sector. Of course, when I wrote this, I was not imagining the Trump revolution. In fact, here, this is the money corrected for inflation that NASA and ESA put on basic science. And as you can see, the NASA money had a couple of peaks, one at the time of many missions, MRO, New Horizon, Stereo, and Fermi, and one is the JWST peak, while the ESA budget stayed more or less constant as a function of the time. But of course, if the cuts proposed by the Trump administration were implemented, we're going to follow that arrow. So not so sure that public funding are more stable than private funding. The standard science mission cost is driven by many things, which I would like to synthesize here. First is we always push our scientific requirements to extreme. with little regard to engineering realities. We want the best, not the sufficient. Minimizing launch mass and volume. This is, I already discussed this. Use of space qualified parts. Failure is not an option. Of course, if you want to apply this point, failure is not an option. You have to be sure that what you have produced doesn't fail. This implies a large number of quality control procedures. In slang, at TISA, we have a huge number of manuals called ACSS, which foresee more than 5,000 requirements for standard missions, mostly on quality standards. Of course, it costs a lot of money and time to be compliant with these standards. In the private sector, you don't have these kind of things. You just build something, you check if it works in space. If it doesn't, you build something else. And then there are quasi-monopoly suppliers, in particular in Europe. You well know, in Europe you have only two main space enterprises, which are Thales Alenia Space and Airbus. And if you look at the ESA missions, there is an alternate prime contractor. One time is Thales, one time is Airbus. Of course, this keeps up the cost. The CubeSat example, I think the most important point from CubeSat is not that they are small. The most important point is that they use a standardization of hardware components. We use standard components. We do not develop components just for that mission. We buy components so-called off the shelf. Of course, this reduces a lot the cost. So what we are thinking is just to apply the same approach, not to small things, but also to big things. Standardization. So what we think is that we should apply the CubeSat and also the Explorer program of NASA approaches to larger spacecrafts. And there are two main steps. We have to rethink the funding space, and we have to rethink the way we do missions, which means we need to find a broader funding base, and we need to work under the three innovation pillars which I discussed before for the private sector. Broadening the funding base. This means to try to understand if the private sector can invest on our scientific missions. This can happen because they want to advertise their activities. This already happens today. Can happen because of profit opportunities in activities such as planetary protection, for example, or exploration of Moon, Mars and asteroids for resource prospecting, or using a science mission to test advanced technologies that they can then apply to their business. And this already is happening. They can buy our knowledge, as was done, for example, by our colleague geologists in the past. Or we can use philanthropic foundations. This was done for building ground-based telescope, as you well know, JAC, for example. Can be done also in space. Why not? We can do public-private partnership. There are at least two very good examples. One is the NASA Commercial Orbital Transportation Service, the service to bring things on the space station by SpaceX and Northrop Grumman, and the Commercial Lunar Payload Service, the CLIPS, to bring things on the moon. Or intergovernmental organization like the European Commission. I used exactly this as a leg of my project Hermes when I won a grant from the European Commission. So this is possible. Innovation. This is more difficult for us. We have to make our requirement smart. because where you end is not where you start, which means that we need to apply in a systematic way an iterative approach to achieve the main scientific goal. We should not think that the mission that we are building today is the final one, like we are used to do. We should arrive to the final goal step by step, with rapid interaction of each step of the development process. This is a change of approach, a change of mind in our field. Before looking for complex technical solutions, we must be sure that they are really necessary to reach the main scientific objective. It's not necessary to build something complicated and costly if this is not necessary to reach our scientific goal. Exploit as much as possible scale production. This is the key. If I buy something that is useful only for me, of course, I pay that things a lot. If I buy something that I can use, but it is built for many other people, that the cost is much, much, much lower. There are examples of this. Starshield, I don't know if you ever heard about Starshield. This is a series of satellites for the Department of Defense. Actually, today it is called the Department of War, the US, that are using Starlink satellite for military purposes. So they are buying Starlink satellite from SpaceX. Remember the table before? Starlink satellite were cost 100 times less than dedicated satellites, 100 times less. So the Department of Defense in the US is doing what I propose to do for science. Or what is proposed by other companies. Here I'm listing two companies. I will show you later what they are doing, K2 and Apex Space. They sell satellites, they sell services. I will show you what they are selling. So let's do a more concrete point on this. This is a paper written 2 years ago by people from Tucson, from the Mirror Lab in Tucson, which is the place in which the mirrors of RBT were done, and by Sol Perlmutter. And what they are writing in this paper is basically the idea of flying a 6.5 meter borosilicate mirror telescope to do science on spectrophotometry on type 1 supernovae at the cost of 300-500 million instead of 10 billion. Is this crazy? Maybe not. You can find in this plot the correlation between the cost and the diameter of mirrors that have flown in the past. And in the upper part of the plot, you find Spitzer, Euclid, Roman, HST, and JWST. And you see that the cost of these missions is huge, from billion to 10 billion. Then in the bottom part of the plot, you find the cost of ground-based telescopes in blue. And in the intermediate part of the plot, you find the cost of commercial telescopes. For example, Planet. Planet is providing the images that you find on your Google map. Skybox, the same. You find also other things like Pandora and Worldview. I will go back again to Pandora in a minute. So that red circle is the goal of these respected people. And they are looking for money to realize this project. And I think it will be revolutionary. Let's go back to slightly smaller things. Here I made an exercise, you see, totaling the order of 50 million euro. And this is not by chance. This is because this is the budget foreseen for the next Italian small space mission. Well, you can reach 50 million, for example, if you buy a satellite, a bus for 10 million. If you build your payload up to 150 kilograms, if you use Apex space buses for 10 million, if you spend other 10 million for system engineering and system AIT for the launch, and even for a precursor, so this is 50 million. So is this crazy to buy a bus for 10 million? Well, doesn't work. No, it works. Okay, so here you go to Apex. You can configure your bus, which is hosting a payload of 150 kilograms. We would like to have an higher power system. We would like to have good communications. Communications are very important. My project failed because of communication. So I would advise you to buy a good communication system. Encryption, doesn't care. We do science. GNC, of course, we want to have a precision package. You see that the price is rising. Then you want to have a bus simulator, of course. We want to have a mechanical interface. We would like to buy services, payload integration, and launch vehicle integration. See, $5,700,000, piece of cake. Okay, so why we should not take advantage of these things while our American colleagues actually take advantage of this? In fact, going back to the presentation, this is what Apex is advertising in their site. A nice telescope on their cheap satellite. And what you can do using this plot is with 50 million is to have a telescope of diameter 60 centimeter. 60 centimeter is the telescope on board the Zeus, or 1 meter. 1 meter is the telescope on board the Ariel. You can do this for 50 million. Why not? In fact, NASA is doing this. This is Pandora. Pandora is going to be launched in a couple of weeks. This is a program started 2021. It is the Pioneer program, enabling cost-effective but impactful science mission. Pandora, 0.45 meter telescope, not too bad, for simultaneous photometric and spectroscopic observations of exoplanet atmospheres. Okay, they are going to launch again in a couple of weeks, not in 2000. When Ariel is going to be launched, the 29. Right. Well, 20 millions, not 500 millions. Okay. This is another example. Escapade. This is going to be launched tomorrow using a Blue Origin New Glenn launcher. These are two spacecraft to be operated in Mars orbit. And the spacecraft are cheap because they are manufactured by Rocket Lab. Rocket Lab is the company that is producing also Electron, this launcher for small satellites. Okay, less than 80 millions included the launch to go to Mars with two spacecraft. Not too bad. Why should we, I mean, Italian, European scientists not to do this kind of things that our American colleagues, they actually are doing since many years? This is the question that we should, on which we should think, okay? Here in Europe, we are probably thinking too much that the fact that, okay, we think at the science, and then ESA or ASI is thinking at how to build the satellite. Well, we should change our mind, definitely. Other things that can be done, of course, is to profit of the whole activity that will be done on the moon. There are 13 currently operational missions more than 40 in the next 5 to 10 years. And even more important, there is already a public-private engagement. For example, the CLIPS project. There is a global interest, not only in the Western world, the Artemis project, but also China and Russia, but also India, Japan, Korea, United Arab Emirates, Australia, Israel, Brazil, South Africa. Everybody wants to go to the moon. The lunar economy moves today 8 to 10 billion per year, and it is foreseen to increase by a factor of 10 in the next 10, 20 years. So we should profit of this, absolutely. This is a picture of a small Japan probes that landed on the moon. For example, there is a lot of activity for moon mining, both for use in space on the moon, water, for example, or use on the Earth. But you can do also a lot of science on the moon. And this is from an ESA report of a few years ago. You can do science off the moon. You can do science on the moon, and you can do science from the moon. For example, radio astronomy, optical and infrared astronomy, cosmic ray astronomy. So we should exploit all these possibilities that are going to be present in the future. And I think I will stop here, but the most important part of the presentation is that I listed 3 pages of references. So if you have time, you can give a look by yourself to find the information that I showed you shortly today. Thank you for your attention.